Welcome to Industrial Inside, your gateway to the hidden world of industrial components and systems. In this video, we'll explore the fascinating world of activated carbon, a versatile material essential to many industrial processes. Let's dive into what it is and why it matters. Activated carbon can be classified by form or by raw material. Common forms include powdered, granular, and pelletized, while sources include coconut shell, coal, and wood. Activated carbon is extremely porous, with a surface area of up to 1,500 square meters per gram. It comes in powder, granular, and pellet forms, and is known for its durability, high density, and low dust generation. Chemically, it has excellent adsorption capacity and contains functional surface groups that can be tailored for specific applications. Just 1 gram of activated carbon and have a surface area equal to an entire soccer field. The steam activation process begins with pre-carbonization, where raw material is heated to 400 to 600 degrees Celsius to remove moisture and volatile compounds. Next, the material is heated to 800 to 1000 degrees in the presence of steam, creating a network of micropores and mesopores essential for adsorption. In chemical activation, the raw material is first soaked in a chemical agent such as phosphoric acid or potassium hydroxide. It is then heated to 450 to 900 degrees Celsius in a low oxygen environment. The chemical reacts with the material, helping form a stable carbon structure with enhanced porosity. Activated carbon has an exceptionally large surface area, typically between 500 and 2,000 square meters per gram, created by its porous structure during activation. This is usually measured using BET analysis with nitrogen gas. Total pore volume, which includes micro, meso, and macropores, usually ranges from 0.2 to 1.0 cubic centimeters per gram, and varies by raw material and process. Activated carbon contains 3 types of pores, each essential for adsorption performance. Micropores, smaller than 2 nanometers, adsorb small molecules and provide most of the surface area. Mesopores, between 2 and 50 nanometers, improve diffusion and support liquid phase applications. Macropores, larger than 50 nanometers, act as transport channels, speeding up access to smaller pores. The iodine number measures how much iodine 1 gram of activated carbon can adsorb, typically reflecting its micropore content. Standard grades range from 600 to 1,200 milligrams per gram, while high-performance types can exceed 1,500. Values below 500 usually indicate low-grade carbon. The CTC value shows how well activated carbon adsorbs VOCs and other gases. It mainly reflects the volume of mesopores and macropores. Standard carbons range from 50 to 70%, while high-performance grades can reach 80%. Adsorption on activated carbon happens when gas or liquid molecules stick to its surface. This can occur through physical forces, chemical bonding, or capillary condensation. Each mechanism depends on how the molecules interact with the carbon. Physical adsorption is the most common type on activated carbon. It uses weak van der Waals forces, not chemical bonds. This process is reversible, works better at low temperatures, and depends heavily on surface area. The more, the better the adsorption. Chemical adsorption forms strong bonds between molecules and the carbon surface. Unlike physical adsorption, it's often irreversible and releases more energy. It's selective, only certain molecules react with active sites on the carbon. Capillary condensation happens when vapor condenses inside the pores of activated carbon, especially in mesopores and macropores. It occurs when vapor pressure inside the pores exceeds the bulk vapor pressure. The process is pressure dependent and reversible. Let's summarize the 3 main adsorption mechanisms. Physical adsorption is weak, reversible, and depends on surface area. Chemical adsorption forms strong, selective bonds and is often irreversible. Capillary condensation occurs in pores due to pressure differences and is also reversible. The adsorption process involves several steps. First, molecules move through the bulk phase. This is bulk diffusion. Then, they pass through a thin boundary layer, called film diffusion. Next is intraparticle diffusion, where molecules travel into the carbon's pores. Finally, they reach the surface and are adsorbed. Let's follow the trip of a contaminant. It starts in a millimeter scale channel, this is bulk diffusion, then moves into a micron scale layer, film diffusion. Next, it travels through 10 nanometer pores, this is intraparticle diffusion. Finally, it reaches a 1 nanometer pore and gets adsorbed. Adsorption capacity, or Q, measures how much mass an adsorbent can hold per unit weight. The equilibrium adsorption capacity, QE, is reached when adsorption and desorption balance out. Breakthrough adsorption capacity shows how much contaminant the adsorbent can hold before it becomes saturated, the breakthrough point. Equilibrium adsorption capacity is the amount of adsorbate adsorbed per unit mass of adsorbent when adsorption and desorption rates are equal. It shows the theoretical maximum adsorption under specific conditions like temperature and concentration. This is measured by batch tests or models such as Langmuir and Freundlich isotherms. It helps compare adsorbent efficiency and understand adsorption behavior. Adsorption is when molecules from gas or liquid stick to an adsorbent's surface through physical or chemical forces. Desorption is the reverse, molecules leave the surface and return to the fluid. When both happen at the same rate, the system reaches dynamic equilibrium. Breakthrough adsorption capacity is the adsorbent's capacity when the output contaminant reaches a set limit, like 0.5% or 5%. It reflects real-world performance in continuous flow systems, considering mass transfer zones and operation limits. Measured from breakthrough curves in column tests, it guides system design and adsorbent replacement timing. Thank you for watching. Please subscribe, share, and comment. Your support is my greatest motivation. This concludes the first part of our activated carbon adsorption series. Stay tuned for the next section.